Welcome back. The learning objective of this video lecture are first to understand the optical properties of CIGS material. Secondly, you will be introduced to the typical cell architectures and CIGS processing methods. In addition, you will learn about the monolithic integration used to interconnect the individual solar cells in a thin film PV module. Finally, alternative cell structures will be presented. The next thin film PV technology we will discuss in this video lectures is based on CIGS. CIGS stands for copper, indium, gallium selenide sulfide. Let's start with the chemical composition and structure of this material. Chalcopyrite materials consist of elements in group 1, 3 and 6. Many combinations of the elements shown here are potential solar cell materials. However, the electronic band gap of most materials is too wide. The most common combination is a mixture of copper indium diselenide or CIS and copper gallium diselenide or CGS. Also, sulfur can be included in the structure, partially replacing the selenide fraction in the material. The typical CIGS alloys are heterogeneous materials. The physical properties of CIGS are rather complex and many different views exist on these properties among scientists. Some important compounds in the material are the copper indium diselenide with a band gap of 1 electron volt, copper indium disulfide having a band gap of 1.5 electron volt, and copper gallium diselenide having a band gap of 1.7 electron volt. These materials cover a wide range of both band gaps and lattice constants. The CIGS material is a direct band gap semiconductor material, therefore it has a large absorption coefficient. It requires only a thickness of 1 to 2 microns to absorb a large fraction of the light above its band gap. Typical electron diffusion lengths are in the same order of a few microns. A variety of CIGS alloys exists, but the best performing layers have something in common. They contain a polycrystalline alpha phase. The lattice atoms are tetrahedrally bonded in this phase. Such a lattice structure is a so-called chalcopyrite structure, as you can see in this illustration. The heterogeneous material consists of a phase of copper indium selenide, often indicated by CIS, and copper indium gallium selenide. Axis 0 means it's a copper gallium diselenide material and axis 1 means it's a copper indium diselenide material. It means using the copper gallium ratio X, the band gap can be tuned from the copper gallium diselenide at 1.7 electron volt to X is 0 down to 1 electron volt for X is 1. The CIGS absorber layer is a p-doped layer. The doping is a result of intrinsic defects in the material related to copper deficiencies as we currently created in the lattice shown. These vacancies efficiently act as an acceptor. It means electrons excited from the valence band can get easily trapped. As a result, the holes become the majority charge carrier densities. Let's look at a typical CIGS solar cell structure. The substrate is glass. On top of the glass, a molybdenum layer will be with a typical thickness of 1 micron is deposited, which acts as the back contact. On that, the p-type CIGS absorber layer is deposited with a thickness ranging from 2 up to 4 microns. The p-n junction is formed by a thin end layer of around 50 nanometers on top of the p-type CIGS that is based on cadmium sulfide. This layer is referred to as the buffer layer. The n-type region is extended with an n-type TCO, and first an intrinsic zinc oxide is placed, followed by an aluminium doped zinc oxide. The aluminum doping makes the zinc oxide N-type. Similar to some concepts of the thin film silicon technology, the aluminum doped zinc oxide acts like a transparent front contact for the solar cell. On top of this, transparent conductive oxide anti-reflective coatings can be placed as discussed for the crystalline silicon technology. Here we see the electronic band diagram of a CIGS solar cell. The light enters the cell from the left at the zinc oxide side. The P-type CIGS absorber layers used in industrial modules have a typical band gap of around 1.1 to 1.2 electron volts. This band gap is accomplished by a ratio of gallium to indium of around 0.3. The N-type cadmium sulfide buffer layer has a band gap of 2.5 electrovolts. Since the band gap of the N and P-type junctions material are different, the CIGS cell can be considered as a heterojunction solar cell as well. The light-excited minority electrons in the CIGS layers have to diffuse to the cadmium sulfide CIGS interface to be separated. The holes diffuse to the molybdenum back contact to be collected. Here the holes recombine with the electrons supplied from this molybdenum back contact. Zinc oxide acts like the front contact. The band gap of the zinc oxide is very large, minimizing the parasitic absorption losses in this device. The electrons have to be separated at the CIGS cadmium sulfide interface. As with every interface, this interface has more defects and could act as a loss mechanism to the minority electrons. This can be prevented by placing an N-type CIGS type of layer between the P-type CIGS and the cadmium sulfide interface, which screens the cadmium sulfide CIGS interface from the holes. The N-type CIGS is an indium-rich alloy like copper, indium, gallium selenide. In copper-deficient P-type CIGS materials, the dominant recombination mechanism is the Shockley-Reed-Hall recombination in the bulk. In contrast, in copper-rich CIGS films, the Shockley-Reed-Hall recombination at the CIGS cadmium sulfide interface becomes dominant. One of the important aspects of the CIGS solar cells is the role of sodium. Low contaminations of sodium appears to increase the conductivity in P-type CIGS materials. It leads to a welcome texture and an increase in the average grain size. The larger the grain size, the less grain boundaries and less recombination are present in the material. This results in higher band gap utilization and higher open circuit voltages. Typical optimum concentration of sodium in the CIGS layers is 0.1%. The sodium source in the growth mechanism can be the soda lime glass used as substrate. In CIGS solar cell concepts, where this soda lime glass is missing, the sodium has to be intentionally added during the deposition process. In the CIGS field, the exact reason why sodium improves several properties of the CIGS is still under debate. In this video, we have discussed the device structure of CIGS technologies. In the next video, I will discuss the processing of CIGS materials, solar cells, and the interconnection in thin film PV modules.